And welcome back, everybody. So in today's video, we are discussing dewatering. So doing an example finally with well field. So this first short video is a general introduction on dewatering of construction site. And then in the next one, I will give a couple of more practical examples, a couple of problems solved in the next short video. So dewatering usually happens when there's a construction site and we wish to do some foundation work, essentially. So here's a little graphic that I took from Verde, which is a construction company, I think down in Peru, I believe. And I like the images because you can really see the installation of the pumping station, the excavation, the piping. You can see the piping here on the bottom right-hand side, and I really like this little graphic here that really shows a cross-section of, the objective of the dewatering, which is to drop that water table. So you can see here the water table, and of course, typically you would have some sheet pile. Some sheet pile, some damming of the site to avoid infiltration as much as possible, and then finally the pumping. You can see these two wells pumping water out of the site so that you can excavate, down and then pour a foundation essentially above the level of the water table. So this is really a typical application of, wells, and typically multiple wells to maintain the water table low. Another couple of schematics, I believe from Feather, from your book. And again, the same idea here, but just on the left-hand side here, illustrating open pumping. So instead of using wells, you can use like ditches basically to excavate or so that the water table is exposed, right? And then if you have a long ditch, then you can just pump, from the ditch directly. So that's open pumping. So that's another option. And here you can see well points. So typically like those well fields for dewatering are made with what we call well points, which are essentially, many small wells or many small pumps, right? Pumping small amount of water out of the construction site. And so here you can see how you have a whole perimeter essentially of wells, that maintain that water table again at a lower level than it would be naturally, which allows you, to do excavation or do some construction at the site. And then you can see here the pumps are in there, and then the whole site is dewatered. Briefly, some review of the mathematics that we can use to solve these kinds of problems. So here again, the steady state, the theorem equation that we've seen over and over in this course, where the drawdown essentially is, Q over 2 pi transmissivity log of the distance, the ratio of the distance of the two observation wells, right? Or we can flip this and then write that the discharge of the well is equivalent to 2 pi kb if we, write the transmissivity as hydraulic conductivity times the depth of the aquifer. Change in drawdown over natural log of the distances. Again, since for multiple wells we use superposition that we've just seen in the past video, we can just sum up, multiple wells together. So again, 2 pi t s, so again, this number here, the top number on this equation, equals the sum of all the q, ln, r2, r1. Okay, right, so this equation here is just 2 pi ts. This top equation here equals the discharge times the natural log, right? So this is the same. Now, r here is the radius of influence. We already talked about this. So radius of influence changes with time typically. And again, in the next short video, I'll do an example where we actually use radius of influence. Note that if all the discharges, so let's say those well points that I just showed a minute ago, right? If all your pumps have the same discharge, then, the equation simplifies. Basically, you can take the discharge out of the summation, right? And you can just say 2 pi ts over q equals, the sum of the ratio of the distances, or the radius of influence divided by the distance. So in the end, right, we simply have that the drawdown, the total drawdown, right, is the sum of the drawdown. So again, it's an illustration of the superposition principle where, you can just use the drawdown for each well and then just sum them up at a point, and that's really simplified to that. One note here for unconfined aquifers, and this is really important, I haven't talked about this yet in this class, is what we call the modified drawdown. So essentially, the trick here, we've seen those equations for confined and unconfined, over and over here. The trick for calculating unconfined aquifer drawdown is to calculate the confined version, which is the simpler version, right? You don't have the squares to worry about. So you calculate the confined drawdown, and then you modify it, if you will, with the stable water table level, right, H0. So the problem with the unconfined, again, is that the water table changes with time, so the thickness is not constant, so that's an issue, right? So if we calculate the drawdown for a confined aquifer with the standard equations, then we can modify that calculation by modifying that drawdown by the stable level, by the water table, if it wasn't moving, right? So the thickness of the saturated aquifer. So here's a quick list of, how to do this. So determine the theoretical confined drawdown, that's what I just explained. So do the sum, right? The resulting sum of the confined drawdown. So if you have several wells, you just do the sum. And then you modify that sum. So again, here S prime is that sum that you found in step 2. So now you modify that sum, right, with H0, which is the thickness of the aquifer before the pumping starts, right? So this is what we call the modified drawdown. And then finally, to know the dewatering component of the drawdown, right, you can subtract the results from 2 and 3, and then that gives you that thickness of dewatering, okay? So this is a method that you can use, and we'll do examples of that in activities. Okay, so just to conclude with this introductory, or this first quick video on dewatering, right, you can see that again we use the principle of superposition. Basically, we use multiple wells to attain, some drawdown at a construction site. Again, I remind you of our little finite difference model in Excel, so we can actually, you could design dewatering plans, using a simple finite difference model or ModFlow or any such model. And again, here another illustration of well points, achieving the dewatering under a construction site where you can do your excavation and then pour your foundation and then, keep on building at that place. Okay, I thank you, and I'll see you in the next video.